Hi everyone, and welcome back to Swift Academy. Today, we are diving into part 4 of our Essential Swift Interview Questions series. If you watched part 3, you know we took a deep dive into memory management, breaking down the exact differences between strong, weak, and unowned references. Today, we are breaking down the dangers of forced unwrapping, navigating threading traps in Grand Central Dispatch, spotting hidden retain cycles, mastering struct versus class mutability, tackling core data persistence, untangling tricky constant initializations, exploring advanced optional safety, passing live code compilation checks, and finally, understanding Swift access control and predicting complex code outputs. Let's kick things off with question number 1. When do we have to use implicitly unwrapped optionals, those exclamation marks in Swift, and why? There are two main scenarios. The first is when using Interface Builder. When a view controller is created in memory, its views haven't been drawn yet. Because those UI elements don't exist at that exact moment. They have to start as nil. Look at the code on the left. We use the exclamation mark to make a promise to the compiler. We are saying, don't worry. The storyboard will connect this button before I ever try to use it in my code. The second scenario is fixing the chicken and egg memory problem. Sometimes two objects absolutely need each other to exist. But who gets created first? If we aren't careful, this creates a nasty retain cycle. To fix this, we use a specific pattern. As you can see in the code, one object, the user, uses an implicitly unwrapped optional so it can briefly be nil. This allows the other object, the profile, to finish building using an unowned reference. This keeps our memory perfectly safe. Moving on to question 2. What is a circular reference in Swift? And what are your options for resolving it? This is a fundamental memory management question that you are guaranteed to hear in an interview. A circular reference, often called a retain cycle, occurs when two instances hold a strong connection to each other. Because Swift uses automatic reference counting, an object cannot be deallocated if it has a strong reference pointing to it. As a result, both instances keep each other alive forever, creating a deadlock and a massive memory leak in your application. To fix this, we simply have to break the chain. We resolve the circular reference by replacing one of the strong connections with either a weak or unowned reference. This tells the compiler not to increase the retain count, allowing both objects to be safely wiped from memory when they are no longer needed. Let's move on to next question. State your understanding of core data. This is a massive Apple framework, but interviewers are looking for a few specific buzzwords to prove you know how it actually works. The biggest mistake developers make is calling it a database. Core data is not a traditional relational database. It is an object graph management framework. It acts as the model layer in your MVC architecture, allowing you to manage, filter, and track data objects directly in memory. Because of this, you don't have to write a single line of SQL. Core data seamlessly connects your app's objects to table records. It automatically handles object storage, validates your property values, and manages the entire lifecycle of your data behind the scenes. Let me know in the comment if you want me to make detailed video on core data. Let's jump to next important question. How many ways can you unwrap an optional in Swift? If you are interviewing for a senior role, don't just list them out. Categorize them by safety to show architectural maturity. Start with the safe methods. Optional binding using if let creates a temporary constant if the value exists. The guard let statement is perfect for early exits. Nil coalescing uses a double question mark to provide a default backup value. And optional chaining lets you safely call properties, returning nil instead of crashing if the object doesn't exist. Next, mention the dangerous methods. Forced unwrapping using an exclamation mark will instantly crash your app if the value is nil. Similarly, implicitly unwrapped optionals are declared with an exclamation mark, letting you skip the if-let checks, but carrying the same crash risk if accessed too early. Finally, drop the hidden gem, the optional pattern. Using if case let with a question mark allows you to beautifully match and unwrap values directly inside enumerations or switch statements. Now that you've flexed your pattern matching skills, interviewers will often zoom out to test your architectural knowledge. That brings us to question 5. What exactly is a Swift module? At its core, a module is just a single unit of code distribution. Think of it like a sealed, neatly packaged shipping container of code that is built and shipped together as one piece. In Apple's ecosystem, every single Xcode build target is treated as its own independent module. So whether you are building a full application, a custom internal framework, or a Swift package, you are building a module. And whenever you need to open one of those containers to use the code inside it, you simply unlock it using the import keyword, just like we do every single day when we type import UI kit. Your code is packaged, but how do you handle heavy lifting without freezing the UI? Let's see the main concept on this in next question. What is Grand Central Dispatch? At its core, GCD is Apple's low-level API for multitasking. Think of it as a traffic controller that takes your code and pushes it into thread-safe dispatch queues, handling everything in a strict first-in first-out order. You need to explain the two types of queues. A serial queue is like a single-lane road. It executes one task at a time, making it perfect for protecting shared resources. A concurrent queue is a multi-lane highway. It fires off multiple tasks at the exact same time, but they finish in a completely unpredictable order. Finally, nail the execution types. Calling a task synchronously blocks the thread until the work is completely done. Calling it asynchronously returns control instantly, so your app can keep running while the work finishes in the background. What will be the value of course1.toughness and course2.toughness? Let's run it. We have a struct course with toughness 3. Line 2, var course1 equals course. We create an instance on the stack. Toughness is 3. Line 3, var course2 equals course1. This is the key. Because course is a struct, it is a value type. Swift doesn't share it. It creates a completely independent copy at a new memory address. Now line 4. Course2.toughness equals 4. You are only changing the copy. So the result. Course1 is still 3. Course2 is 4. But what if we change struct to class? Now course is a reference type. It lives on the heap. Var course2 equals course1 no longer copies the value. Copies the reference. Both variables now point to the exact same object. So when you set course2.toughness equals 4, you are changing that one shared object. The result. Both course1 and course2 are 4. Same address shared. So remember this for your interview. Structs are copied. Classes are shared. Struct gives you 3 and 4. Class gives you 4 and 4. Here's a classic Swift interview question. Will view2.alpha equals 0.7 compile? We declared view1 with var and view2 with let. Setting alpha on view1 is easy, but what happens when we try to mutate view2? To answer this, look at how memory handles reference types. With var view1, the stack holds a mutable reference pointing to a UI view object on the heap. Because it's a var, you can change the view's properties, and you can even reassign view1 to point to a completely new UI view. Now look at stage 2 with let view2. Let creates an immutable reference slot on the stack, meaning the pointer address itself is locked and cannot be reassigned. But the UI view object sitting on the heap is still fully mutable. So changing alpha compiles without any issues. So the final answer is yes, it compiles. The key insight here is that for classes and reference types, let only locks the pointer on the stack. The object on the heap stays mutable. You only need var if you plan to reassign that pointer to a different instance later. Take a look at this Swift code snippet. We have a temperature struct and we are trying to update its value. Will this code compile? The short answer is no, and it actually fails for two distinct reasons. First, structs are value types. If you want a method to modify an internal property like temp, you absolutely must mark that method with a mutating keyword. The code provided completely misses this. But even if we fix the function, the compiler will still throw an error on the last line. Why? Because the instance was declared using let. Unlike classes, when you use let on a value type, the entire object becomes strictly immutable. You cannot call a mutating method on a constant, you have to change it to a var. Can you predict the output of this Swift program? We set an item to apples, define a closure that prints it using a capture list, change the item to oranges, and then call the closure. Does it print apples or oranges? The secret lies entirely in those square brackets, the capture list. When you put a value type inside a capture list, Swift takes a permanent snapshot of its value at the exact moment the closure is defined. Creates an independent constant clone. Because it created an independent value copy, when we mutate the original variable to oranges on line 5, the closure completely ignores it. Its captured version is safely locked in as apples. Therefore, when we finally execute the closure, the final output is, he wanted to eat apples. Remember, capture lists freeze the value. If we hadn't used those brackets, it would have captured by reference and printed oranges instead. Mastering memory concepts like this is the key to passing senior iOS interviews. Thank you so much for watching. Drop a like if this helped, and I'll see you in the next one.